We've never seen anything like this in the solar system. Is it a freak in space? Since a landmark discovery in 1992 of 2 planets orbiting a star outside of our solar system, thousands of new worlds have been added to a rapidly growing list of exoplanets in the Milky Way galaxy, our galaxy that is. We've learned many things from the vast catalog of alien worlds orbiting alien stars, but one small detail stands out like a sore thumb. We've found nothing else out there like our own solar system. This had led some to conclude that our home star and its brood could be outliers in some way, perhaps the only planetary system of its kind. By extension, this could mean life itself is an outlier, that the conditions that formed Earth and its veneer of self-replicating chemistry are difficult to replicate. If you're just looking at the numbers, the outlook is grim. By a large margin, the most numerous exoplanets we've identified to date are a type not known to be conductive of life. They're giants, they're subgiants, and of gas and may be very icy. Most exoplanets we've seen so far orbit their stars very closely, practically hugging them, so close that their sizzling temperatures would be much higher than the known habitability range. It's possible that as we continue searching, the statistics will balance out and we'll see more places that remind us of our own backyard, but the issue is much more complex than just looking at numbers. Exoplanet science is limited by the capabilities of our technology. More than that, our impression of the true variety of alien worlds risks being limited by our own imagination. What's really out there in the Milky Way galaxy and beyond may be very different from what we actually see. Expectations and how to thwart them. Exoplanet science has a history of subverting expectations right from the very beginning. If you go back to that world I grew up in when I was a kid, we only knew of one planetary system. Planetary scientist John T. Horner of University of Southern Queensland told Science Alert, saying, and so that was kind of implicit assumption, and sometimes the explicit assumption that all planetary systems would be like ours. You know, you'd have rocky planets near the star, and where we're quite small, you'd have gas giants a long way from the star that were quite big, and that's how planetary systems would be. For this reason, it took scientists a while to identify an exoplanet orbiting a main sequence star like our Sun. Assuming other solar systems were like ours, the telltale signs of heavyweight planets tugging on their stars would take years to observe, just as it takes our own gas giants years to complete an orbit. Based on such lengthy periods of single measurement, it did not seem worth the trouble to sift through a relatively short history of observations for many stars to conclusively sift out a fellow main sequence solar system. When they finally did look, the exoplanet they found was nothing like what they were expecting. A gas giant half the mass and twice the size of Jupiter, orbiting so close to its hot star, its year equals 4.2 days, and its atmosphere scorches at temperatures around 1,000 degrees Celsius, that's 1,800 degrees Fahrenheit. Since then, we've learned these hot Jupiter-type planets are not oddities at all. If anything, they seem relatively common. We know now that there's a lot more variety out there in the galaxy than what we see in our home system. However, it's important to note not to assume that what we can currently detect is all that the Milky Way has to offer. If there's anything out there like our own solar system, it's very possibly beyond our detection capabilities. Horner said things like the solar system are very hard for us to find. They're a bit beyond us technologically at the minute. The terrestrial planets would be very unlikely to be picked up from any of the surveys we've done so far. You're very unlikely to be able to find a Mercury, Venus, Earth, and Mars around a star like the Sun. How to find a planet? Let's be perfectly clear, the methods we use to detect exoplanets are incredibly clever. They are currently 2 that are the workhorses of the exoplanet detection toolkit. the transit method and the radial velocity method. In both cases, you need a telescope sensitive to very minute changes in the light of a star. The signals each are looking for, however, could not be more different. For the transit method, you'll need a telescope that can keep a star fixed in its view for a sustained period of time. That's why instruments such as NASA's space-based Transiting Exoplanet Survey Satellite TESS is such a powerhouse, capable of locking onto a segment of the sky for over 27 days without being interrupted by Earth's rotation. The aim for these kinds of telescopes is to spot the signal of a transit when an exoplanet passes between us and its host star, like a tiny cloud blotting out the few rays of sunshine. These dips in light are tiny, as you can imagine, and one blip is insufficient to confidentially infer the presence of an exoplanet. There are many things that can dim a star's light, many of which are one-off events. Multiple transits, especially ones that exhibit regular periodicity, are the gold standard. Therefore, larger exoplanets that are on short orbital periods closer to the stars than Mercury is to the Sun, so much closer on orbits of less than 1 Earth week, are favored in the data. The radial velocity method detects the wobble of the star caused by the gravitational pull of the exoplanet as it swings around in its orbit. A planetary system, you see, does not really orbit a star so much as dance in a coordinated shuffle. The star and the planets orbit a mutual center of gravity known as the barycenter, and for the solar system, that's a point very close to the surface of the Sun, or just outside it, primarily due to the influence of Jupiter, which is more than twice the mass of all the rest of the planets combined. Unlike a transit's blink and you miss it event, the shift in the star's position is an ongoing change that does not require constant monitoring to notice, and we can detect the motion of distant stars orbiting their barycenters because that motion changes their light due to something called the Doppler effect. As a star moves towards us, the waves of light coming in our direction are squished slightly towards the bluer end of the spectrum. As it moves away, the waves stretch towards the redder end. A regular wobble of the star's light suggests the presence of an orbital companion. Again, the data tends to favor larger planets that exert a stronger gravitational influence or shorter, closer orbits to their star. Aside from these two prominent methods, it's possible on occasion to directly image an exoplanet as it orbits a star. Though an extremely difficult thing to do, it may become more common in the James West telescope era. According to astronomer Daniel Bayliss of the University of Warwick in the UK, this approach would uncover an almost opposite class of exoplanets to the short orbit variety. In order to see an exoplanet without it being swamped by the glare of its parent star, the two bodies need to have a very wide separation. This means the direct imaging approach favors planets on relatively long orbits. However, larger exoplanets would still be spotted more easily through this method for obvious reasons. Bayliss said, each of the discovery methods has its own biases. Earth, with its year-long loop around the Sun, sits between the orbital extremes favored by different detection techniques, he said, so to find planets with a one-year orbit is still very difficult. And what's out there? By far the most numerous group of exoplanets is a class that is not even represented in the solar system. That's the mini Neptune gas-enveloped exoplanets that are smaller than Neptune and larger than Earth in size. Most of the confirmed exoplanets are on much shorter orbits than Earth. In fact, more than half have orbits of less than 20 days. Most of the exoplanets we've found orbit solitary stars much like our Sun. Fewer than 10% are in multi-star systems, yet most of the stars in the Milky Way are members of a multi-star system, which estimates as high as 80% seen in a partnership orbiting at least one the other. Think about that for a moment, though. Does that mean that exoplanets are more common around single stars, or that exoplanets are harder to detect around multiple stars? The presence of more than one source of light can distort or obscure the very similar but much smaller signals we're trying to detect from exoplanets, but it might also be reasoned that multi-star systems complicate planet formation in some way. And this brings us back home again, back to our solar system. As odd as our home seems in the context of everything we found, it might not be uncommon at all. I think it's fair enough to say that there's actually some very common types of planets that are missing from our solar system, said Bayliss. Super-Earths that look a little bit like Earth, but have double the radius. We don't have anything like that. We don't have these mini Neptunes, so I think it's fair enough to say that there are some very common planets that we don't see in our own solar system. Now, whether that makes our solar system rare or not, I think I wouldn't go that far, because there could be a lot of other stars that have a solar system type set of planets that we just don't see yet. On the brink of discovery, the first exoplanets were discovered just 30 years ago orbiting a pulsar, a star completely unlike our own. And since then, the technology has improved out of sight. Now that scientists know what to look for, they can devise better and better ways to find them around a greater diversity of stars. And as the technology advances, so too will our ability to find smaller and smaller worlds. This means that exoplanet science could be on the brink of discovering thousands of worlds hidden from our current view. As Homer, the ancient Greek, points out, in astronomy, there are way more small things than big things. Red dwarf stars are a perfect example. They're the most common type of star in the Milky Way, and they're tiny, up to about half the mass of the Sun. They're so small and dim that we can't see them with the naked eye, yet they account for up to 75% of all stars in the galaxy. Right now, when it comes to statistically understanding exoplanets, we're operating with incomplete information because there are types of worlds we just can't see. That is bound to change. I just have this nagging feeling that if you come back in 20 years' time, you look at all those statements that mini Neptunes are the most common kind of planets with about as much skepticism as you'd look back at statements from the early 1990s that said you'd only get rocky planets next to the star. Now, I could tell you we'd be proved wrong. This is how science works, but my thinking is that when we get to the point that we can discover things that are Earth-sized and smaller, we'll find that there are more things that are Earth-sized and smaller than there are things that are Neptune-sized. And maybe we'll find that our oddball little planetary system, in all its quirks and wonders, isn't so alone in the cosmos after all. This is an earlier version of an article published December 2022, and this is on Science Alert by Michelle Starr. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.